All right, so we're going to be talking about chapter 7.5, using proportional relationships. One of the important ideas with similar triangles is this concept of indirect measurement. Indirect measurement is anytime you use sort of geometric properties to find the length or size of something. Um, you can see here it's similar figures, proportions. We'll learn how to use indirect measurement techniques with trigonometry in future sections. Anything that allows us to calculate something that seems not possible to measure by some other technique. So here's a quick example here. A student wanted to find the height of a statue of a pineapple. So find the height of this thing. Looks really tall. Not super easy to just bring out a tape measure or something and calculate and measure it that way. So you can do another technique here. Um, she measured the pineapple shadow and she measured her own shadow. If the student's height is 5 feet 4 inches, what's the height of the pineapple? Well, fortunately for us, we know all kinds of things about triangle similarity. And if we imagine the sun up here, casting its rays down, right? These triangles have one right angle right here, because we always measure height at a right angle to the ground, perpendicular. And the way the sun's rays come in at a constant, kind of angle, we know that the angle that gets created here, that kind of works on creating that shadow, is also going to be congruent. So we do know that we'll have similar triangles here. That's great. That means we can use proportional relationships. We'll go ahead and solve this in the next slide. So I'm not going to rest this out here. All right, so let's actually start solving this. One important feature here is that the student's height is given in this mixed units of 5 feet 4 inches. Generally, you want to make sure you stick with just sort of one unit. If I was looking at being really precise here, I would convert everything into inches. That way I don't have to do any rounding. I can just, or any decimals or anything. I can just work with whole numbers, but I'm just going to get some decimals. I'm going to assume as a decimal that this is around 5.33 feet. Just a small assumption I'm making. It's not exactly that. Technically, it's 5.3 repeating, but I'm going to go ahead and round it to this point, and that's her height. Another thing, the shadow of the pineapple was again measured in feet and inches, so this one works out. I don't have to do any rounding. That's exactly 8.75 feet. And the thing we're missing here is the height of the pineapple. We'll call it h. Okay. Fortunately for us, again, we remember that we have some similar triangles here. We have the right angles, and then we have that angle created by the sunshine as well. So these are similar triangles, so we can set up a proportion. When you're setting up a proportion, you do need to make sure you set it up in a consistent manner. I'm going to make sure I do like shadow over shadow, height over height, and then either pick both measurements from the girl to be on top or both measurements from the pineapple, but make sure I do that as consistent. So I'm going to set mine up this way. It's going to be 2, which is the girl's shadow. That corresponds with the shadow of the pineapple, 8.75. And then the height of the girl, 5.33, over the height of the pineapple, h. That's the unknown. Again, setup here is very important. It's very important that it's consistent. There are many ways you can set this up. This isn't the only way, but it is one way. Again, I have the measurement of the girl on top, her shadow, measurement of the pineapple on the bottom, pineapple shadow, girl's height, pineapple's height. It's that consistency that we're looking for. Cross multiply, we get 2h equals, do this calculation real quick, 8.75 times 5.33. That's 46.6375. Divide everything here by 2, and we find the height is, and I'm going to round this. I'm going to say this is approximately 23.3 feet. It's my number I got here is 23.31875. On the test, I'll tell you specifically how I want you to round your answer. I believe I tell you to round the nearest tenth on the test, so 1 decimal place. But again, pay attention to how the answer is requested. There's nothing given to us about the form of our answer, but we'll just go with this here. It's 23.3 feet. All right, let's go ahead and move forward. Very similar problem here about shadows and flagpoles. So a student who is 5 feet 6 inches tall, that's exactly 5.5 feet, measured shadows to find the height of a flagpole. So we're looking for the height of this flagpole. Not very easy just to measure that, so you can use similar triangles here. So we have 5 feet for his shadow, 5.5 feet for his height, 14 feet 2 inches, 14 plus 2 over 12. So that's around approximately 14.17 feet. Again, I'm rounding here. It's actually 0.16 repeating, but I'm just going to round this. If I want to be more precise, I should probably convert everything to inches and go that way, but I'm just looking for an approximation, so we'll keep it the way we have it. All right, we're setting up proportion here. So consistency is key. We're going to do the shadows in our first proportion. So shadow of the person over the shadow of the pole. So person on top and the pole is going on bottom. And now the height of the person goes on top and the height of the pole goes on the bottom. Again, consistency here. Shadows in this one, heights in this one, person on top, pole on bottom, person on top, pole on bottom. Consistency is what matters here, not necessarily the exact location of everything. Cross multiplying, we get 5h equals 77.935. And then we divide that by 5, divide everything by 5. So we get our height is 15.587. And again, rounding the nearest tenth, we could call this 15.6 feet. We could also try to calculate the amount of inches that this decimal represents. So we could do 0.587 times 12 to get feet and inches. So that's around 7 inches. So we could say it's 15 feet 7 inches. A lot of different ways we could go with this. I'm just going to go with the easy decimal, 1 decimal place in feet. Doesn't matter though. All right, let's go ahead and move forward. Okay, a lot of words here, a lot of things going on. We've already learned some of this stuff, but let's focus on these two things right here. Just talking about what similarity ratio is and what the perimeter ratio is. So the similarity ratio is simply the ratio of corresponding sides. When you have similar triangles, that is always going to be constant, right? The ratio of corresponding sides will be a constant if the triangles are similar, which in this case they are. 5 over 10, 4 over 8, 3 over 6, all of those give us a half. Well, it turns out the ratio of the perimeters follow that same ratio. So the similarity ratio for our triangles is going to be the same as our similarity ratio of their perimeters. Because if we add all these up, we get a perimeter of 12 and a perimeter of 24. 12 over 24, same ratio. That always works, doesn't matter. The ratio of the sides is going to match the ratio of the perimeter. That kind of makes sense. I mean, we calculate the perimeter just by adding up the sides, so why wouldn't they follow the same rules? The area, however, is a bit misbehaving, and it's because area is done by multiplying. We multiply some things together, and thus it messes things up a little bit. Turns out the area of these, the smaller triangle, the area of this is 6. 3 times 4 divided by 2 is 6. And the area of the bigger one is 24. 6 times 8 divided by 2 They have a ratio of 1/4. So the area ratio is 1/4, different than the perimeter and different than the sides. Why? Well, it's because if I split this up into 4 triangles, you can see there are 1, 2, 3, 4 of these, of this, right? There's 4 of these triangles inside of that. So the area is 4 times greater. It's just the way it works. Turns out it's just the similarity ratio squared. So whatever our similarity ratio is, if you square it, that's your area ratio. Kind of a cool thing. You can see that down here as well. We're going to kind of use that to help us solve some problems. I think it'll make more sense as we look at and solve problems using it. Okay, so here we have 2 similar triangles. It is very important we know that they are similar. We can use the sides to figure out the similarity ratio. So similarity ratio. So our similarity ratio here is 16 to 20. Obviously that reduces. They're both divisible by 4, so we get 4 to 5. So this is our similarity ratio. It's also our perimeter ratio. Because we know those things are the same. The similarity ratio and the perimeter ratio are the same. Well, it turns out we can actually use that to solve for the perimeter of this larger figure. I know the perimeter of this one, so I can use that to solve this. Our perimeter ratio has to be equal to the ratio of the perimeters. The 4 is a smaller number, the 5 is the bigger number. The 4 goes with the smaller figure, the 5 goes with the bigger figure. So the ratio here of our smaller one, 36, over the bigger one, which is unknown. Smaller, bigger, right? We matched it up in that consistent manner. We can go ahead and solve for the perimeter of this larger figure. We get 4p equals 5 times 36. It's 180. Divided by 4, we get 45. So the perimeter of this shape is 45 feet. Pretty cool. Again, we're just using the similarity ratio and setting up with our perimeters, one that we know and one that we don't, that we have to solve for. Again, keep in mind with these that the smaller number goes with the smaller figure, the bigger number goes with the bigger figure. So we can set, that's the way to set up the second part. All right, and then the next piece here is we want to find the area. So what is our area ratio? Well, our area ratio is always found by taking our similarity ratio and squaring it, raising it to the second power. So 4 to the second power is 16. 5 to the second power is 25. So this is my area ratio. This doesn't reduce, so we have to leave it like that. We can use it to set up a proportion, though. I can use this known area and an unknown area to figure it out. 16 to 25 is equal to 48 to A. It's important that consistency. The 16 goes with the smaller figure. The 25 goes with the bigger figure. So 48, smaller figure, A, bigger figure. Matter of solving this, cross multiplying, 16A equals 1200 divided by 16. The area here is equal to 75. 75 feet squared. That is our area. Kind of cool. You got to make sure you use the area ratio when you're working with the areas and the similarity ratio when you're either working with the sides or the perimeter. We'll go ahead and do one more of those. Oh, we'll go back. Okay, so this one is cool. We don't really have a picture, but it's good to be able to draw that. Again, we know we're working with 2 similar triangles, so let's just go ahead and draw 2 triangles. One smaller than the other one. Looking at these measurements, BC, EF, looks like ABC is smaller because this number is smaller than this number, but so I'm just going to make that assumption that the first one is smaller. And let's just label things to make it easy to work with. So we'll call this A, B, C, and then we'll match that up D, E, F, right? A corresponds to D, B corresponds to E, C corresponds with F. Again, we don't know the actual size of these things. I'm just drawing some triangles just to sort of help this process. All right, now let's label it. BC is 4 millimeters. EF is 12 millimeters. If perimeter equals 42 millimeters and area equals 96 millimeters for triangle DEF. Oh, okay, so that's for triangle DEF. B equals 42, A equals 96. Okay, cool. So this is pretty similar to what we did on the last problem. Only difference is we actually know the measurements of our larger triangle here. What is the similarity ratio? Well, our similarity ratio is 4 to 12. 4 to 12. And obviously that reduces. Both of those are divisible by 4, so it reduces to 1 to 3. This is our similarity ratio. We'll call it a sim ratio for short. Or that's also for our perimeters as well, our perimeter ratio. So let's go ahead and find the perimeter of this smaller shape. Okay, well, 1 to 3 has to equal, where do things go, right? So 1 goes with the smaller figure, 3 goes with the bigger figure. So 1 and P, unknown. Those need to be in the same place on the top together. And then 42 and 3. Because again, 1 kind of matches up with our smaller shape, 3 goes with our bigger one. Since we don't know the perimeter of the smaller one, that's going to be unknown. And then, yeah, sorry, it should be 42. Did not write that down correctly. And it just becomes a matter of solving this, cross multiplying. 3P equals 42. So P equals 14. So 14 millimeters. Okay, similar idea. Keep doing that. Yeah. What's our area ratio? Area ratio. So our area ratio is going to be 1 over 3 squared, which gives us 1 over 9. All right, so let's use that to set up a proportion. We have 1 over 9. Again, the 1 corresponds to the smaller one. The 9 corresponds to the bigger one. So we don't know this area. So this is our unknown. And this one is 96. Cool. Cross multiply. 9a equals 96. 96 divided by 9. So the area of our smaller figure here is 10.6 repeating millimeters squared. So things to keep in mind with these type of problems. Make sure you know whether you're going to be using the area ratio, right? If you're trying to solve for area, then use your area ratio. Or you're using your similarity ratio. So that's for the sides or the perimeter. This is for area. Another thing to do that is when you do go to set up your proportions like this, make sure things match up in a corresponding way. Use your area or similarity ratio and make sure the second one matches up. The smaller number goes with the perimeter or area of the smaller figure. Bigger number goes with the perimeter or area of the bigger figure. There we go. All right, make sure you guys get to work on those 2 quizzes. So from last week, 7.1 and 7.2, and then the new one from this week. See you guys in class.